Okay, so after finish the divergence theorem, we'll also talk about the Stokes theorem. Okay, so this is another type of the fundamental theorem of calculus. So here we have a line integral, which is like this is 1 times of integration, and this is a double integral. Double integral is like 2 times of integration, and then here we have a curl. Curl is still like 1 times of derivative. 1 times of derivative. So it's also like 2 times of integration. Cancel one of the derivative, become a first integration. But here we need the curl operator rather than a simple derivative. So here we have a curl taken to the field and then take the double integral, and then it is actually the same as the line integral. Okay, so it says that the line integral of a vector field over the boundary of a surface equals the surface integral of the curl vector over that surface. Of course, yeah. So here is about the physical meaning. So suppose this is the contour. This is the contour. And here we will try to consider the line integral. The line integral is like over this path, and then you just keep calculating like this is ds, and then maybe this is f. So this is like f dot ds, and then you just calculate over the whole contour, and then it is actually equal to curl of f, and then over this whole surface. So as I mentioned, the curl of f is like you try to see how everything is rotating, for the whole region. And if it is like rotating like this, so you can see for adjacent point, this rotating is like this is pointing downward, this is pointing upward. So in between, all the things will be cancelled. So the only remaining stuff is the over the boundary of this contour. So yeah, this is a quick explanation for the physical meaning. So we try to take the curl over the region and then integrating, which means we consider all the rotating for the whole thing. And then the inside part will cancel. The only remaining part is over the boundary. So it turns out to be this line integral. Of course, this will become a scalar. Okay. So, and also, if you would like to know how we can derive it, then you can refer to the link. Okay, so here we can try to apply the divergence theorem and Stokes theorem to really derive the differential form of the Maxwell equation. So first is the Gauss law for electricity, and yeah. So here we have the Gauss law for the electricity. Originally, it's like the surface integral equals Q enclosed over epsilon naught. And as I mentioned, we try to write this Q enclosed as a triple integral. Okay, so we have this one equals this triple integral. Okay, so by the divergence theorem, we have the surface integral equals the triple integral of the divergence of the same vector field. Okay, so we can see that this one and this one are the same, which means that this one is equal to this one. Okay, so we can see here, we put this one here and put this one on the right side. And also we try to put this one inside because it is just a constant. You can just place it inside. Okay, so here we have a triple integral of this stuff over the dv, and then we still have triple integral dv for the same thing. And then actually, although I mean originally we cannot really write the integrand are equal, but it will be true for arbitrary Gaussian surface we have chosen. So in that sense, we can really say that the integrand itself equals each other. So as much as the Gaussian surface can be arbitrarily chosen. Arbitrary chosen. So it turns out that the integrand itself should be the same. So it turns out to be divergence of E equals rho over epsilon naught. So this is the first differential form for the Gauss law. And similarly, for the Gauss law for magnetism, which is like integration of B dot dA equals 0. So that's why we have this one. Okay, so quickly we can use the divergence theorem to convert the integration from or integral form of the Gauss law to be these two PDE. And then for the Faraday's law, it is easier than the Ampere's law, so we do it first. Okay, so this is a Faraday's law. So this is line integral of the E field. On the right side, it is a partial d dt. This is phi b. This is phi b, and then we try to write it explicitly. Okay, so according to the Stokes theorem, we have the line integral equals the double integral of the curl of this vector field. Okay, so here we can see that this one and this one are the same. So this one should be equal to this one. Okay, so here we place this one here equals this one placing here. Okay, then here we will try to move this derivative inside the integration side. So one small detail is like this is the original derivative. This is the partial derivative. Why is like this? Why? The reason is originally B field should be a vector. B field should be a vector related to x, y, z, and also t. It depends on the position. X, y, z are the position. This is the time. For every point in the space, if you plug in a certain x, y, z coordinate and also the time, then it defines the B field at that moment, at that position. Okay, so B should be a function of x, y, z, and t. But if we already take the inner product, so after taking this inner product, it becomes this B dot dA should only be something related to time, because it already dot with if the dA, it becomes a scalar, and this scalar should only related to the time, because the position information already absorbed by this dot product and summation. The integration is like you add many times. Okay, so this turns out to be a function of time. This integration turns out to be a function of time. So we can use original derivative. But if we put this one inside, of course for mathematics, they need to consider whether this thing converges. For some specific things, if you try to do it first and then do the integration later, just swap the order of the operation. For some specific function, they may be different, but for most of the case, and this is engineering case, swapping the order of the differentiation or integration is usually okay. So here, try to do this thing first. So we try to put this thing inside, but putting the derivative inside, which means that B is a function of x, y, z, and t. It's a function of 4 independent variables. So here we need to use the partial derivative rather than an original derivative. Okay, so in that case, we have the extreme left side equal to the extreme right side. And similarly, as much as we can arbitrarily choose the ambient loop, we can arbitrarily choose the ambient loop, which means that the integrand should equal to each other, which means that this curl of E should be negative, this partial B partial T. So this is the differential form of the Faraday's law. And yeah, and for the Ampere's law, it is a bit more difficult, actually a bit different. Okay, so this is line integral of the B field, and then on the right side, this is mu naught, this is I enclosed, this is the displacement current. Okay, so using the Stokes theorem, line integral of B field is double integral of curl of B. Okay, so here we can see this one equals this one, and then so this one equals this one. So we put this thing on the left side and then put this one on the right side. And then we try to put this mu0 inside. Put this one inside, put this one inside. So it turns out to be mu0j. So we have mu0j here. And then we have mu0 epsilon naught. And then we also put this one inside. So it turns out to be partial E partial T, similar to the previous one. So we have a mu0 epsilon naught partial E partial T all in, okay, this whole thing inside this double integral. And then as I mentioned before, you can arbitrarily choose the ambient loop, which means that the integrand itself should be the same. So here we have a curl of B equals this thing. This is the differential form of the Ampere law. Okay, so here we try to really explain how we can use the Stokes theorem, and also the divergence theorem and Stokes theorem to really derive this thing, the integral form of the Maxwell equation to the differential form of the Maxwell equation. Okay, so an interesting story is that Stokes, when you know Stokes is actually at that time is a professor, and then he really invented this Stokes theorem, and then in the exam he tried to ask the student to really prove this Stokes theorem. Of course, at that time almost no one can really prove this one, because maybe 100 and something years ago, they don't have such a good systematic textbook. So at the time, most of the students can't really prove this Stokes theorem in the exam. Only one student can really prove this one. The one is actually Maxwell. So this is an interesting story, and actually Maxwell used the Stokes theorem to really derive the differential form of the Maxwell equation. Of course, all the law are not invented by Maxwell. As you know, these two are called Gauss law. Of course, invented by Gauss, and then this is invented by Faraday. This one maybe half of it related to Maxwell, but the one who tried to group all the useful formula together is actually Maxwell. So it's around 1855. It's around that year that Maxwell really developed the theory of the electromagnetism to be the Maxwell equation. Okay, so before finishing this part, I try also to explain the relationship between Maxwell equation and the conservation of charge. Of course, in very early in this semester, in chapter 21, we have already mentioned conservation of charge in a very shed away, just like we cannot create a charge, we cannot vanish a charge. Yeah, but actually we can use a partial differential equation to describe what is conservation of charge like this. Oh, what is that? Okay, so here I also would like to explain why this strange equation is actually the conservation of charge. Okay, so let's start from some definition we are familiar with. So first is the current and the charge density. Okay, so here we have a negative sign. So which means that, and also we have a circle here for the double integral, which means that we try to define a Gaussian surface. Of course in 3D, but I can only draw it in 2D. So suppose we have a region. You can assume is a sphere. Okay, so we define this is a Gaussian surface, and then within it is a sphere. Okay, so here we try to consider the current density and the current. Okay, so the charge density has a negative sign. Yeah, so it feels like if there are some current going out, that which means that there are some electron going into this region, which makes the charge density to be larger, something like this. So here we have a negative sign. So yeah, and according to the this is actually the divergence theorem. Okay, we have this double integral equal to the triple integral of divergence of J. We just put this negative inside, so this negative doesn't relate to the divergence theorem. The divergence theorem only changed this double integral into a triple integral, but we also need to add the divergence to the current density. Okay, so yeah, so we have this I to be this triple integral, and also I equals dq dt. So similarly, Q can be written as a triple integral of the current density. Okay, so Q become a triple integral, and we also try to put this derivative inside. So it becomes triple integral of a partial derivative of the charge density with respect to time. Okay, so this is I, so these two equals to each other. And as much as you can arbitrarily choose the Gaussian surface, which means that the integrand itself should equal to each other. So which means that partial rho partial t plus gradient of j equals 0. So it means that if we have some current density flowing outside, and it will change the charge density. Yeah, because current density means there is some current. The current really means that the charge is moving with respect to time. Yeah, as much as the charge is moving with respect to time, we have current, which means that if we have charge density, the change of charge density, which means that if there are some current flowing outside, then the charge density will reduce. So if this increase, this will reduce. If this reduce, this will increase. They sum up to be a 0. This is so-called the conservation of charge, which means that if the charge density inside this region is increasing, there must be some current flowing into this area, and vice versa. So this is, so we can call this one is the conservation of charge. And how does it relate to the Maxwell equation is that, okay, suppose yeah, we have the Ampere's law as this one. Yeah, only up to this part. Maybe not. Okay, let me try to write it again. So for the Ampere's law, it is like gradient. Curl of B equals mu naught J, and then plus epsilon naught partial E partial T. So this is the Ampere's law. And then we try to take this is a vector field. This is also a vector field. So we can try to take divergence on both sides. It becomes a scalar field. Okay, so we try to take divergence on both sides. And then I can let you know that this curl of divergence of a vector should always be 0, no matter what this B is. Okay, you can verify by yourself. You can just, for example, you can write this B into a Bx I hat plus a By j hat plus a Bz k hat, and then you refer to the original definition. You know, this is like the determinant. We will have 6 terms, and then you try to take the divergence again. So it will be very simple. It's just like here. Okay, here. Then you try to take divergence to it, which makes it like partial f z, and then partial x partial y, and then minus partial square f y, and then partial x partial z. Okay, so this is the first 2 terms, and then you can do it for the following 3. Then you will turn out find that they will cancel each other. Just say this term. We also will have this one taking the partial derivative with respect to y. So it turns out to be partial to partial fz, and then partial x partial y. So this one and this one are actually the same, but this one with a negative sign, so they will cancel. So you can clearly verify that no matter what the vector field is, the curl and then the divergence of it, the divergence of curl of a vector should always be 0, which means that this is 0. So the only remaining is the right side, and then here. Yeah, so here we can just put a divergence of J. Divergence of J is here. Divergence of, so we put this divergence inside the partial derivative. It turns out to be divergence of E, and then partial T, and then times epsilon naught. And then also according to the Gauss law, divergence of E is this thing, which means that we just replace this one. Replace this divergence of E by rho over epsilon naught. So this epsilon naught and epsilon naught will cancel each other. It turns out to be partial rho partial T. Okay, if we just plug in this one there, this term will become partial rho partial T. And then for the first one, it is nothing but mu naught divergence of J plus partial rho partial T. And then of course, mu naught is not 0, so we can just cancel it. It turns out to be partial rho partial T plus a gradient of J to be 0, which is actually the conservation of charge. Which means that if Ampere's law is up to this format, it is consistent with the conservation of charge. That's why we don't really further add some other terms to it, add the 3rd term, 4th term to it to make it more correct. Because if we further add some other else to it, then it will probably violate the conservation of charge. But conservation of charge should be true. So yeah, so up to this part, this is the Ampere's law.